to be back here. Okay, so I'm going to be talking about algebraic geometry in MATLib, and you will see that it's not really the most beginner-friendly area to work on, but luckily, algebraic geometry uses a lot of structures from commutative algebra, and ultimately, most of the things you do in algebraic geometry are commutative algebra, and commutative algebra is very, very user-friendly, I think. So I'll give a very quick overview of actual things that involve schemes and affine schemes at the beginning, but then I'm going to switch and talk about more sort of polynomials, algebraic objects, because those are eventually what you're going to be working on. So I'm going to give you a quick overview of how algebraic geometry fits inside MATLib. So the blue dot is algebraic geometry. Don't pay too much attention at how this graph looks like, because I don't exactly know how it was generated, in the sense that I don't know whether all the errors that are in there are just covering edges or any possible thing. But it should give you an idea. These are the main folders that you have if you download MATLib. There's some folders within the MATLib folder, and each dot represents one of those folders, and the arrows are supposed to represent vague dependencies among them, probably exact dependencies among them, but I don't know exactly the fine details of how this graph is built. But anyway, this is where algebraic geometry stands inside MATLib. These are the files within the algebraic geometry folder. Okay, so I guess there's a couple of things that I want to point out. Yeah.
And just quickly, I haven't seen a number of such graphs. Are these graphs also somewhere available, like in the online documentation, or?
So there is a command line interface to generate these graphs. So you can type import graph, and then you can give it some options to display other things, and it would produce an output file that then GraphViz can visualize for you. So because it takes 2 steps, I don't exactly know what information is encoded in which. So, but I generated these by basically running import graph, editing the output, and then passing it to GraphViz. And I got these visualizations. They looked kind of reasonable. I thought they're good enough representation where people are not going to be looking at exactly each edge and figuring out, is it really a dependency there, okay? So they should be. I don't know whether they literally are, okay? But there might be some small mistakes, but there is this command called import graph that, that sort of tries to do and construct these graphs for you. All right, so what I want, have I answered your question? Is it okay? Yeah, okay. So, by the way, I also learned about this while presenting the talk, and this is why you're going to see 3 or 4 slides with pictures like this, because I thought it was cool. Okay, so what I want to talk about this picture, what I want to highlight is, well, first of all, it has 2 connected components. There is algebraic geometry here, and then there is elliptic curves here. Okay? And you see that they're sort of in separate parts of the algebraic geometry repository. And somehow I would say that the big connected component is developing the theory so that later on people would be able to work as in algebraic geometry with things like elliptic curves. But people had an itch for working with elliptic curves. So they defined elliptic curves disregarding anything about sheaves, structure sheaves, schemes, anything. They just defined elliptic curves to be the list of coefficients of a Weierstrass equation for them. And then they played with that. So once enough of the machinery of the sort of big connected component here arrives at the stage where you can define curves, you can define affine curves, projective curves, I'm guessing that this smaller piece of the graph will be engulfed in the bigger one, okay? But right now it isn't. And I think this is also representative of what my presentation is going to be. I'm going to give you an overview of the big connected component, a very quick one. And then I'm going to switch to doing something like in the small connected component, but it won't be about elliptic curves. Okay? It'll be something that is close to what could be done correctly, but it's just sort of the this algebraic groundwork that goes into doing something that has to do with algebraic geometry. So that was one of the things that I wanted to mention about this graph. The other thing is what I'm going to be importing for this graph to show you what I'm going to show to you is a projective spectrum scheme, which, as you can see, is probably a leaf of this graph. There's nothing coming out of it. It imports a bunch of the stuff above it, but nothing below it. And affine scheme, which is further down. An affine scheme then branches off further into properties about morphisms and other things. So that leads somewhere else in this graph. Of course, both will grow, presumably. But these are the two imports that I'm going to be using. And these are sort of minimal imports for what I'm going to be talking about. OK, and if you notice, this is scheme. It's further up here. Affine schemes import schemes because, of course, an affine scheme is a scheme that happens to be affine. And so you sort of use schemes before you define schemes before you define affine schemes. And then there's some numerology about how many files there are in the algebraic geometry folder, how many files there are in mathlib, how many lines of code. It roughly seems correct, about 100 times, sorry. OK, I didn't say this. If you have any questions, please stop and ask me questions. I don't really have anywhere that I want to reach, so. OK, so this is another of these graphs that, as I said, that generated because I like the fact that I could generate it. So the blue dots now are all the algebraic geometry files. The green dots are any file that has a direct dependency from the algebraic geometry side. Okay, maybe. But you can see that there's sort of something. It becomes sort of noisy and random eventually. This is what algebraic geometry imports from ring theory. So one of the big imports for algebraic geometry. This is what algebraic geometry imports from algebra, a little bit less. People haven't developed very much the scheme of the sort of relative scheme, so there's not a lot of algebras over other things yet, but there might be. And so this is a recap. So now you know how many files in each of these directories is imported directly by something in the algebraic geometry folder. Okay, so it gives you an idea of where algebraic geometry sits within math or within mathlib. And you see that the biggest number of imports are from ring theory. Then there's something from topology, category theory, which I'm going to be talking about a little bit. Category theory is actually hidden inside algebra and ring theory as well, because some of the ring theory and algebra theory are algebra.category something else. So there's more category theory than what this seems to give away. And there's sort of the random import from linear algebra, tactic, and data. Okay, so this is how it looks like. If you get bored, you can look at which one is the file from tactic that is imported and which one is the file from data that is imported. Okay, so now this is what I was trying to get at the beginning. So most of the big connected component of algebraic geometry uses a lot of category theory. And category theory is, as you've also heard yesterday Jakob mention, is, I think, an inherently non-beginner friendly area of mathlib. And I view the reason for this arising from two main issues, in that it deals explicitly with universe levels. You really have to be careful about defining things in the correct universes for things to work. And it deals explicitly with type class inference. Okay? So you sort of build the bundled category of semi-rings or commutative rings, and then you sort of build arrows between them. So you have to somehow get your hands on a little bit of controlling type class inference. You have to be careful about this. And both universe levels and the type class are what very often in the rest of mathlib is just done hidden from you and secretly behind the scenes by Lean itself. Okay? So you have to start understanding a little bit of how you use these things that normally you never get to grips with. Okay? Nothing is especially complicated. In fact, it's so easy to deal with them that the computer does it in the background, and usually you don't notice about it. So there's algorithms that do this, and they work fairly well. But when you start messing with it, you have to start understanding how these things work. And it's just something that usually you don't see when you begin doing stuff in mathlib. So that's one of the reasons why these things are difficult. And so as a consequence, I'm not going to try to rely too much, in fact, anything on category theory, which means we're going to stay in sort of the scattered connected components of the algebraic geometry graph, and we're not going to deal exactly with the big one. Okay. Any questions? All right, so what is algebraic geometry and why does it need so many other things? Now, I honestly don't think that it needs so many things, but you would need to use those things if you wanted to use the Mathlib library. Okay? So, but algebraic geometry takes algebraic objects, specifically in math, commutative rings with one, in Mathlib, well, maybe the same, but presumably people will start removing hypotheses like commutativity, existence of one, associativity. But anyway, it takes one of these things and tries to extract information from it. And it turns out that the information you extract from it is conveniently packaged into something that is really algebraic and something that is more topological. And the topological side is what's usually called the spectrum or the prime spectrum, or sort of that's a topological space that is associated to it. And on top of that space, you build a sheaf of algebras, rings, modules, whatever, in order to study the ring that you started with itself. Okay? So ultimately, everything is guided by rings, and that's why a lot of it is commutative algebra. But the language to study this involves a little bit of topology, a little bit of commutative algebra, and a lot of category theory to glue these things together. Okay? So in my presentation, I'm going to focus on the ring side, which is probably what most people, or at least certainly what I consider to be more algebraic geometry. I don't do a lot of category theoretical algebraic geometry. I was once called, oh, you're such an Italian algebraic geometer. And yes, I am. So you won't see any categories in the kind of algebraic geometry that I do. All right, so let's continue. So this is a quick recap. If you've never heard these words, it probably won't tell you much, but maybe give you some idea. If you have heard these words, well, maybe you already know what I'm saying. But basically, you start with a ring. You construct a topological space called the spectrum of the ring, denoted by spec R. And it's a topological space that is built out of the prime ideals of your ring. Okay? So it's nothing particularly esoteric. The sheaf of rings on it is basically the functions that you want to consider on this topological space, and what you want to consider to be a continuous function. And as you can guess, it's polynomials, essentially. You're allowed to do divisions, because when you remove stuff, the things that vanished on that thing now suddenly become invertible. And so you can do some division, but basically it's the same thing as the ring itself with some elements inverted. And then you put these two together and you get an affine scheme. And I'm saying this just because when I'm going to go to the coding part, I will click on the definition of scheme or affine scheme, and you will see that it's a pair consisting of one thing and another thing. And one thing is a scheme, and the other one is well, sorry, I'm getting confused about affine schemes and scheme. You'll see that a scheme is a pair of two things. It's a topological space, and then the statement that's locally affine. Okay. And so basically, this slide is setting me up for when I will click on the corresponding definition in Mathlib, I will tell you, you see, I've told you that this was going to happen. Okay, so if you knew what these things are, you'll think, oh, yeah, that's so cool. And if you didn't know about these things, you'll still be left with, oh, I didn't remember what you said before anyway, so it doesn't matter. And in any case, it doesn't matter for solving the exercises either, so don't worry about it if you're not following. All right, so this is a recap of this. So we start with a ring, we build stuff out of it, and then we prove stuff about this ring by basically reconverting it back into ring statements. But presumably these ring statements we get at the end are easier than the ring statements we had at the beginning. And so we end up proving some complicated property of rings by proving some simpler property of rings. But the conversion between these two goes through a lot of extra machinery. But ultimately, this is what we want to do. And now I'm going to show you how affine space over field, this is what's usually denoted by AN, is embedded into Mathlib. So now I'm going to switch to the coding part and open a terminal. I think the next slides are just sort of the minted text. So I'm just going to switch over to the other side. Are there any questions before I move on? It's not necessarily a good sign. So, oh, I might still be sharing the screen because I see that second.
Yeah, you're supposed to be sharing.
Okay. All right. So this is what algebraic geometry looks like in Lean. From far, it doesn't look very different from anything else in Lean. But anyway, so as I said, these are the two imports that I'm using: affine scheme and projective spectrum dot scheme. We have a non-computable section here. As you can imagine, we're not going to get the computer to do any computation for us, so we don't really care about this. And I'm going to open. So we've seen this command other times. So open means that then we have access to shorter names for stuff, but it also gives us hints of what it is that we're going to be using. So we're going to be opening algebraic geometry. Fine, we're in the algebraic geometry folder. That sounds surprising. We're going to be opening schemes. Of course, I'm going to be talking about schemes. We're going to be opening comring cat. That's the category of commutative rings. Again, if you know a little bit of algebraic geometry, you know that affine schemes and the opposite category of commutative rings are the same in mathematics. In Lean, they're not the same, but they're equivalent. So it's kind of reasonable that if you want to go a little bit inside schemes, you'll have to be seeing something about commutative rings and their category. And opposite, because in fact, when I was saying the previous thing, I did mention that it was the opposite category of well, either the opposite category of schemes that is isomorphic to the category of commutative rings, or the opposite category of commutative rings, maybe more typically, is the category of schemes. Sorry, affine schemes. Okay, so now the very first thing that you run into when you try to use the algebraic geometry library is that you have to put a lot of two-letter words sprinkled around to make things even type check. Okay. So this first abbreviation that I've written here is how you would write this if you were a mathematician, and what you would have to write in Lean to achieve the same thing. Okay. So here I'm defining that when you see spec of a commutative ring, mathlib should really parse scheme.spec.obj. So that's the underlying object of the spectrum of a scheme. And then you see that you have to put this of R. Of R really means you take R, the commutative ring, and you think of it as a commutative ring. So an element in the category of commutative rings, and that of converts a ring, a type with a commutative ring instance into an object of the commutative ring category. So this takes us from the type R to the commutative ring R in the commutative ring, in the commutative ring category. Op unimaginably converts this object of the category of commutative rings into an object of the opposite category of commutative rings, because that's where we're really starting from. And then of that, we can take the scheme. Oh, sorry, the spectrum. Okay, so that's what it's doing. It's not hard, but if you didn't know that you needed to use of and op, and of course, these are just the shorter names we have. I would have written opposite.op, as you can see when you hover, and here I should have written comringcat.op. Okay, but you don't want to do that, and you don't do it because you've written the open beforehand, but you still need to put all of this. Without any of these, this doesn't type check. Okay, so you really need to put both. And so I've given myself a shorter name. I write just spec of R, and it just means, oh, you have to take the opposite, and you have to put it in the right category. Okay, so just easier to type things. And so then we can define the n-dimensional affine space over the field R. And I'm defining it to be this Unicode symbol bold A, which is what you would use in math. And then you give it the field, so K is a field, and you give it an n, natural number, and it's supposed to give back to us a scheme. And the scheme that it's supposed to give us back is the spec. This is this spec that I've just defined up here. It's the spec of the multivariate polynomial ring on n variables with coefficients in K. Okay, so it's the spectrum of the polynomial ring. It's just mostly what you would say in math. It just sort of converted literally into Lean. Okay, any questions? So because I said this, let's look at what scheme is. I mean, we've built a term of something, but we have no idea what scheme is. So let me just go and see if I can jump to definition. So you see, scheme extends a locally ringed space. So it's some topological data, the locally ringed space, with sheaves on it. And the extra property that we want, besides it being a locally ringed space, is that it's locally affine. So for every point in the corresponding locally ringed space, there is an open neighborhood of that point and a ring such that that open neighborhood is isomorphic to the spectrum of that ring. And this statement is converted into this non-empty, there exists an open embedding. So we're asserting that there is some open embedding of the spectrum of this thing into the target locally ringed space. Okay, it's just sort of a lot of tricks to get this to work, but basically we're saying it's a locally ringed space that is locally affine, and that is the definition that you would have in math. And then of course you can go and look at what locally ringed space is, and you would get a topological space with a sheaf of rings that are local rings, and so on. Yeah.
On this align command, because I think we've seen this on
yeah. Sorry, this align command is a consequence of the porting of mathlib from lean 3 to lean 4. So align has on the left what used to be what still is the mathlib 3 name of that same declaration. And on the right-hand side, there is the new name that this sort of same definition has in mathlib 4. This is useful because once you align things like this, then the script automatically knows that whenever it finds the name on the left, it converts it to the name on the right. So because there was a capitalization stuff that happened, all of the names changed, and it wasn't easy to do this entirely automatically, and this was a good trade-off between having to do it and you just do it once, basically. Any more questions? Yeah.
So how does it see here that open neighborhoods correspond to open neighborhoods in some topological space or something?
So it's in this non-empty. So in mathematics, you very often say there is something. And sometimes when you say there is something, you really mean, I know exactly what functions you're going to be using, but I just care about the existence. So I'm not going to tell you that I define this function and then I check that it exists. But other times you say there exists something and you really mean, I don't really care. I cannot even define it because maybe I'm defining it using the axiom of choice. So this non-empty stumbling block here is to let you know that it doesn't really matter which one you choose. Okay, so you're asserting that the type of isomorphisms between the two things that you see later is non-empty. So there is somewhere some isomorphism, and you're never going to care about literally what it is. Okay? You can extract one if you want, but you don't need to, and usually you're not going to have to use any properties of that thing other than the fact that it is an isomorphism between those two things. And the thing between it is an isomorphism is the restriction of the locally ringed space to the open set U of X that we fixed, and the spectrum of, well, maybe the reason is that this wasn't showing entirely. And the spectrum of, you take the ring R, you convert it into its opposite, you take the spectrum of this, and then you take the associated locally ringed space. So we're saying the locally ringed space associated to the spectrum of the ring is isomorphic to some open neighborhood of the point where we are. And we're formulating this in such a way that the isomorphism between the two is completely hidden inside some garbage data. Is it clear now? In fact, it's not even data. That's the main point. All right. Any more questions? All right. So let me switch back. I didn't want to do that. Okay. All right, so now that we've unfolded this, now spec of multivariate polynomial over the finite set with n elements and the field K conveys some idea, maybe. It seems close to what you would say in math, at least of the first layer of unfolding. We've checked that it's what you would expect from that, if you were expecting anything. And then, of course, you would have to go further layers down to make sure that, well, local ring space means what it means, no, open neighborhoods mean what they mean, and spectrum means what it means. But okay, so it's some layer. And so after we've done that, we can check that AQ of 4 type checks. Okay? So I'm claiming that this is the 4-dimensional affine space over the rational numbers. Okay? Now, because I tend to do things that involve number theory, I didn't think of using the complex numbers here when I wrote these lines. But then I thought, oh, but maybe people there don't care about algebraic, don't care about number theory, so maybe they want to work with the complex numbers. So I could change this Q to C. So let me try this. So now you find that this is no longer type checked. And the reason is that none of this mathlib category imports anything that has to do with complex numbers. Okay? So it just doesn't know what C is. Okay? So I'm going to switch back to Q.
But you could import.
I could import C. Yeah, I just didn't know what was the import because I found out about this when I didn't have access to a computer. So anyway, I could increase my imports and make it work for C. It was going to work for any field. In fact, if I go here and I change field to com ring, what do I need? I failed to synthesize. Oh, sorry. I didn't want to change it here. I want to change it in the definition. Well, okay, I'm going to leave it here. So now it doesn't type check. But if I change in the definition of the affine space, if I decide, oh, but I really want to work with the affine space over a commutative ring, it still works. Okay? Now, I don't think you can actually go below that, but soon people were going to start working with semi-rings and their spectra, and then you could probably weaken that a little bit and get something out of that. Anyway, this is one nice thing about lean, I think, is that if you decide that you want to change the definition, you just change it and see what breaks. And if something breaks, then you fix it. If it doesn't break, then, oh, I never used that assumption. Okay? I didn't use the fact that K was a field. I just used the fact that it was a commutative ring. All right, so now let me give you a flavor of how you would fail to find things about stuff in the category theory library, well, or in algebraic geometry. Okay, so let's say that I take K, which is a commutative ring, and okay, I guess I'll see what happens here, but I'm guessing it's going to work out. And I want to check, is it affine? Okay, so it should be because I built it as the spectrum of something. Okay. So the first thing that I'm going to try is, as usual, so the first things that you should try are exact, and then simp, then dsimp, and then you try to do what might work. Exact doesn't work. Okay. Now that's not so surprising because I've just made the definition that A is that previous thing. So there's no lemma in the library that will ever mention A anywhere. Okay. So maybe I was too optimistic about exact working here. So let's first unfold the definition of A. Okay, so now when I unfold the definition of A, lean is going to replace the is affine A to is affine whatever A meant. Okay, which looks worse to us, but it looks better to lean because now exact works. And exact now suggests, oh, you meant spec is affine, whatever else needs to go there. Okay, and then we're happy and we use it. Okay. Notice that I didn't test this beforehand. I had fields before in here, and it worked, and it still works without fields. Okay, so that's the magic of type classes happening in the background for us. Okay. Lean knows that it only needed of the field instance I've given it. It only needed a com ring. So when I then switch field to com ring, I'm just making its life easier. It's not going to have to decide that a field is actually a commutative ring. It just knows it needs a commutative ring. It finds a commutative ring. Okay. So then we might be interested in defining the k-valued points of a scheme. That's something that people do. And it's just a fancy name for all the morphisms from the spectrum of a field to the ring we have, to the scheme we have. In this case, we're just going to go to a random scheme X. Okay, so this would be spec of K. Spec, remember, it's our abbreviation of op of whatever. So it's and this arrow here is not the arrow of implication. It's the hom in a quiver arrow. So it's the set of all maps as schemes between the spectrum of K and X. And the unfolding of stuff that we're going to be doing explicitly is what happens here. So in this example, I want to show that to have a ring homomorphism from R to K, which is what I start with, this F here, means that I automatically have a K-valued point of the spectrum of R with values in K. Okay? That's not at all a surprising fact. It's basically the definition, and Lean knows that it's basically the definition. But you see that I have to use this exoteric command change. So they're equal in the sense that they're definitionally equal, but they're not the same. So in fact, if here I didn't try change to begin with, but I tried exact, I don't think that this would work, right? So Lean doesn't know that these two things are the same right away. However, I'm not sure it works after either, but let me see. However, if I change the, so you see change is going to take the target, which is this K-valued points of K with values in R, sorry, of R with values in K. I change it to be, oh, sorry, I clicked the wrong arrow. I changed it to be, just give me the arrow. Sorry, I changed it at F. Sorry, I was looking at the wrong thing. Look at what happens to the F line here. So the F line goes from being a ring homomorphism from R to K. It goes to being, well, it's still a ring homomorphism from R to K, but now it's in the category of commutative rings. Okay. A morphism between R and K in the category of commutative rings is exactly a ring homomorphism.
What was it before?
It was the arrow with plus dot, with plus star.
Yeah, what is that?
This is, oh, sorry. This is a ring hom. So it's a function, so it's a bundled function. So it's a function from R to K that happens to preserve addition, multiplication, 1, I guess 0, and maybe that's it. I hope that it was presented in some earlier talk.
In my tutorial, talk about ring homs, but I didn't mention anything about rotation.
I see. Oh, so maybe you would have preferred, you would have preferred to see here. This is exactly the same. This is ring hom R to K. Okay, and it does, I mean, I find the notation better, but it's just notation on top of what ring hom is.
The change does what?
Right, so the change just informs Lean that a morphism in the category of commutative rings between a ring and another ring is a ring hom between them. Okay, so if you see, in fact, it didn't matter. So I changed the ring hom in the declaration at the beginning, in the type of in the statement, but Lean still displays it to me as R arrow plus star K. If you look at, right, so. So that the notation overrides whatever I've written there. It just pretty prints like this. But when I do the change, I'm doing something that makes Lean more aware of stuff. Okay. In fact, if I didn't do this change, oh, sorry, in this case, it does work. So, okay, I think I had a previous version where it didn't work, or maybe it didn't work when I had field above. I don't know. But anyway.
So is change for the homomorphism what off is for the ring?
Right, sorry. Maybe I should have, maybe parentheses here help. So this is how you should parse it. And I'm going to put an extra layer of parentheses here. Okay, so I'm changing F to be of R arrow of K. Okay.
I still have one more question. So now this is supposed to be an arrow in category, but I thought we learned yesterday that in categories you always use a different kind of arrow which goes in the diagram direction rather than.
Oh, but I'm not composing any. If I were to compose two of these, I would use the sort of greater sign, and I would write them in the other order. But I'm not composing anything. I'm just changing one arrow to another arrow. I think I had a point about this, but I can't remember what it was, because I don't seem to need this change. So all of this discussion has been just to teach you something, but it wasn't really needed for this case. I think I had some reason for mentioning this, but oh yeah, exact didn't work. Yeah, okay, maybe that's all that it was. But the point is that exact doesn't work here either. So I don't know what it was. Maybe I got confused myself at some. I got myself confused at some point. Yeah. No. So okay, maybe I'll make a more global comment about change. So in maths, and more relevantly in Lean, when you make definitions, you pile on top of previous ones. Okay, and sometimes you make a new definition, which is just the same as the old one, but you just prefer to look at it a little bit different. Okay? So Lean is able or unable, depending on its settings, and you can change this, to see through definitions. But usually it tries not to see too deep, because you're presumably mentioning two things that are close to one another, just like in math. When you're talking about the natural numbers in math and you're doing inductions on them, you're rarely thinking about them as the empty set, the set containing the empty set. You're thinking about them in a more abstract way. You're not unfolding the definition of natural number until it becomes a set of sets of sets. And in Lean, the same thing happens. When I'm dealing with schemes, I often don't want to unfold the definition of scheme so that it's a pair of a topological space and a spectrum and whatever. So with the change command, you can access a little bit of this, and you can tell, look, in this case, I want you to go up or down, or up in one way and down in another part of the declaration, so that now you don't have to do any further unfolding and just get that what you have is exactly what you want on the other side without even having to do any unfolding. Okay? So change often helps when two definitions should be the same, two definitions are the same, Lean isn't seeing it, and then you tell it, oh, but here I'm using the fact that one in the ring of matrices, one is the diagonal matrix that only has ones, and so when you see a one there, you might as well pretend it was. I'm not sure whether this example really needs unfolding, but sometimes you do. And in fact, you see that it has visible effect on what you see. Before the change, this was an arrow with a plus and a star, and then it becomes a long arrow in category theory. So.
Another question. So there's also this explicit type conversion. Is this somehow related, or how? I mean, could I also have written F colon and then of R to of K?
Oh, here. Yeah, oh, yeah. I think so.
No, not here. So, sorry. One line below. If I want to consider F now as a morphism of categories.
That's what I think. So I need to put the of, because, oh, you're saying, do I need the of? I think you do.
No, that's not my question. I want to write, say, let G colon, let G equal.
You're not going to give him the type, yeah?
Parenthesis, F colon, now of R to of.
Oh, this.
Yes, exactly.
I think this would work. Let me try. Let's try.
Okay. Yeah.
Yeah, because Lean sees that type annotation. It uses it to learn how to read it, and then it throws it away. But if you put it off to the left, then it will remember it.
Sorry.
Yeah, you put it there instead, then it will work.
Oh, yeah.
Also, if you make k-value points in a grid, or you unfold it on line 48, then the exact might work.
Sorry, if I do what?
If you make k-value points on line 39 and a grid rather than a depth,
yeah.
you can see through it, then the exact question mark might work. Still with change. Well,
I'm going to try it with and without.
Okay,
okay, let's see without. All right, so I was clever enough to know what it should have been exact. Okay, but anyway. Sorry? No, I think if you do apply spec map, it might, well, let's see. Sorry, this keyboard confuses me. oh, sorry. These zeros were meant to be. So now it tells me that it's F. Let me see if I remove the G, but I think, oh, yeah. Yeah. But in any way, I had to feed it some extra information. Okay? I don't really know why I did this. I can't remember why I did it, but anyway. Any more questions about this? All right, so then let me just say briefly something about proj. If you start with a graded algebra, you can construct its proj. Now, in MATLib, I don't think there is yet the proj as a projective scheme, but there is the fact that you get a locally ringed space out of the proj of something. And I think there is also proofs of the fact that it is covered by open affines, but it just hasn't been glued together nicely. And I think part of the reason for this is that there's been, in the port, category theory and algebraic geometry suffered a big issue. So I think people are trying to solve the previous issues before developing more of the category theory and the scheme theory and part of algebraic geometry of MATLib. So here you could, I just defined for you what the proj of graded algebra is, and like above, but I only defined it as a locally ringed scheme. It's not as a scheme or as a projective scheme, as you might want, but this type checks. Okay. I realize that I'm very short on time, so I just want to go quickly over the exercises that I prepared. The exercises are here. So these are the ones without the solutions. So just as a quick thing, I've written a very small thing. I hope Eric is no longer paying attention now, so that I say that these scripts give you suggestions. In fact, they take all the tactics that are used in my solutions of those exercises and take all the lemmas that I use in those exercises, and they just give them to you. So if you type help, you get both the tactics and the lemmas that I used. If you just type tactics or just type lemmas, you just get one or the other. Okay? And you can do this either as a command or inside when you're proving something. Okay? It might be useful, it might not be useful. I didn't realize that there was already a help command in MATLib. So, I mean, it doesn't clash, but I don't know if it's going to create some issues. I shouldn't have called it help. I just didn't know that there was one. I found this out because someone asked about it before when I started traveling. Okay. And then, so I would have gone through all of this part. I guess you're going to go over it on your own if you want to work with these exercises. Basically, you cover polynomials. Polynomials in MATLib are not particularly strange. There's just basically two things you have to remember, that when you open polynomial, R of x works as a notation. So R is a semi-ring, and then you put square brackets x around it, and it gives you the polynomial ring in R in one variable. The variable is called x. The constants, you embed them into the polynomial ring by using C. Okay, so C of R times S, where R and S are elements of the ring, is the product of R and S in the ring thought of as a polynomial of degree 0. And x is just the variable x. There's also monomial. We never really use monomial, so it doesn't really matter. And then here is an example of how you could compute the square of x plus c1. So this would be x plus 1 squared, just written in lean. And you check that it's the same as x plus 2 times x plus 1. The point of this is that I didn't use the c on the right-hand side. I just directly used the numeral. Now, natural numbers are special, and lean interprets them specially, so you don't need to put a c here. I could have put a c here, but the proof would have probably broken down. Oh, no, it won't, because I used simp. Okay, but other proofs might break. So that was one of the caveats that I had here, that you have to be careful. Lean is going to try to remove the c's for you when it can. That's not always a good idea. So sometimes it just doesn't work. And then there's degrees, so not degrees of polynomials, and something about, so this is the comment about the c's, and then something about add monoid algebras. These are just group rings. Okay, so there's the beginning part is has solutions possibly given in terms of exacts, And then the exercises begin here, and you have all the stories that you have to fill in. They might be hard, so do ask questions. All right, my time is up. Any questions? Yeah?
How difficult is it to define functors from, let's say, games to something else? Is there also some simplification algorithm where you just define what as an object and morphisms, and then the rest is checked automatically?
Right. So a lot of the times, just giving it, if the functor you're defining is easy enough. So in general, for any functor between any two categories, AESOP-CAT will try to fill in all of the fields that you don't actually have to give. Whether or not it will succeed, it depends on how complicated the functor you're trying to define is. Okay, so for forgetful functors, it should work. I don't know how much of the opposite in it it's going to work with. Presumably it will, because that's usually not a big deal. But if you're doing something more complicated than that, well, it just depends on whether AESOP was programmed enough to do it. My guess is if there is a little bit of math content to what you're trying to do, it will not work. If there is no mathematical content to what you're trying to do, it may work. Sometimes it doesn't work because there was mathematical content, you just hadn't realized it. But sometimes it's just there wasn't and there still isn't after you solved it.
So, if I understand correctly, projective space does not yet really exist in the scheme?
Right, so I don't, sorry.
Just there exists some kind of this basic version. I mean, I just want to say what projective space over C, and then have elements of that and computations with them. Very basic level.
Right. So depending on what you mean by computation, a lot of this part of the library is non-computable. So if by computation you mean all right, okay. So then those kinds of computations you should be able to do. But I think the route that has been decided to for projective varieties is to go via defining first projective morphisms. And defining projective morphisms is more complicated than just using proj and then working with this. So I think that's one of the reasons why proj of a commutative algebra is not yet a projective scheme, is that projective schemes haven't been defined because projective morphisms are just being developed. If I switch back to the presentation, I think there was, where is it? Here. If you see, after scheme, there's properties, and you can see these are what is available. So universally closed is there, but I don't think quasi-separated, quasi-compact, open immersion, finite type. So this is closing in on projective, but it's not there yet. It might be that you might be able to say that it's complete before you're able to say that it's the PN is complete before you're able to say that it's projective, but I don't know.
I guess my question is whether I'm really, as you were saying, I'm more thinking almost on the ring side. I just want to do some basic things like I have some ordinate given A colon B.
My guess is that rather than using the big connected component is to do, in fact, what I do in the exercises. Let me then show you one of the things. You see, in the exercises, I define this notation spec that takes a ring and then in round brackets another ring, and it gives you the ring homomorphisms between them. Okay, these are the S-valued points of spec R. Okay, they aren't R in the sense of they are in the morphisms in the category of it, but they're very close to that. And you can prove, for instance, that, well, a bunch of random things. And then one of the exercises, it shows that, where is it? Yeah, that if you look at the spectrum of the group algebra of the group Z mod 2, that it has at most 2 elements. You know it's x squared minus 1, so x plus 1 or x minus 1. It has 2 points. Okay, it's not very deep, but you can do it.
We do have elementary projectivization. If you're content to work over a division ring, we have, you know,
Right, and I think what I'm suggesting here is do something closer to that, because before the other thing takes over, it's going to take time. Yeah.
So we have this group schemes actions, like you said, how do we have a group algebra?
Sorry, this is the group algebra, it's not the group scheme. So an add monoid algebra takes a ring and an additive group and builds for you the group algebra of that group with coefficients in that ring. Okay, so when I write this Z mod n is Z mod n, okay, so just spelled differently, but it's the same. So when you write, where is it? Here. R, and also notice this is custom notation for this to make it look more like math. This would be add monoid algebra, and also because I never remember the order. I think this is add monoid algebra R Z mod 2, but it might be the other way around. But it's the add monoid algebra, so formal linear combinations with coefficients in R and terms you're multiplying by in Z mod 2. So this is the polynomial ring in one variable, x divided by x squared is 1, because that's the relation in Z mod 2. Okay? So this is a way of leveraging the add monoid algebra API, which is fairly big, to do a quotient of polynomial rings, k of x modulo x squared minus 1. Okay? It's a trade-off. You could do it either way. I think this is easier than working with the quotient ring. But of course, if you want to divide by a more complicated relation, it won't be an add monoid algebra. It will really be a quotient of rings, and then you will have no choice. So I think people are trying to do that, but I think currently there are more basic issues of the fact that working with the algebraic geometry and category theory files is just really slow. So you have to wait 5 minutes for a declaration to type check. So I think people are trying to make it speed up before they can actually everything has been ported before they can develop more the machinery. So I think it's a little bit of an unpleasant moment in this area, because you need some computer science issue to be fixed before you can actually keep on developing the mathematical side of this. This is what formalization is about. The mathematicians need the computer scientists to make things fast, and the computer scientists need the mathematicians to sort of figure out what it is that we like to do. Any more questions? All right, so thank you.